Welcome to this problem-solving session. Today, we'll tackle LeetCode problem number 1681, titled Minimum Incompatibility. We'll explore how to efficiently divide an array into subsets while minimizing incompatibility. Let's dive in. In this problem, we are tasked with dividing an integer array nums of length n into k subsets of equal size. Each subset will have a size of m, which is calculated as m equals n/k. Once the array is divided, we calculate the incompatibility of each subset, which is defined as the difference between the maximum and minimum elements in that subset. The goal is to minimize the total incompatibility, which is the sum of these individual incompatibilities across all subsets. If it is not possible to divide the array into the required number of subsets, we should return -1. The input consists of the array nums and the integer k, and the output will be a single integer representing the minimum total incompatibility, or -1 if the division is not feasible. Let's consider an example to better understand the problem. Suppose nums is 1, 2, 1, 4, and k is 2. Here, the size of each subset is m equals n/k equals 4/2 equals 2. One possible way to divide nums is into the subsets 1, 2, 1, 4. For the first subset, 1, 2, the incompatibility is calculated as 2, 1 equals 1. For the second subset, 1, 4, the incompatibility is 4, 1 equals 3. Adding these values together gives us a total incompatibility of 1 plus 3 equals 4. This is one valid division of the array, and the output in this case is 4, as it is the minimum total incompatibility. This division of the subsets represents the minimum possible total incompatibility for the given input. Now, let's look at another example. Suppose nums is 6, 3, 8, 1, 3, 1, 2, 2, and k is 4. The size of each subset here is m equals n/k equals 8/4 equals 2. One way to divide the array is into the subsets 1, 2, 1, 3, 2, 3, 6, 8. Looking at the incompatibility of each subset, the first subset, 1, 2, has an incompatibility of 2, 1 equals 1, and the second subset, 1, 3, has an incompatibility of 3, 1 equals 2. Continuing with this example, the third subset, 2, 3, has an incompatibility of 3, 2 equals 1, and the fourth subset, 6, 8, has an incompatibility of 8, 6 equals 2. Adding these values together, the total incompatibility is 1 plus 2 plus 1 plus 2 equals 6. This is the minimum possible total incompatibility for this input. Now, consider another example where nums is 5, 3, 3, 6, 3, 3, and k is 3. In this case, it is impossible to divide the array into k equals 3 subsets of equal size without having duplicate elements in the same subset. Therefore, the output is -1, as the division cannot be completed under the given constraints. Finally, let's review the constraints and edge cases for this problem. The constraints specify that the length of the array n is divisible by k, ensuring that the subsets can potentially have equal sizes. Each number in nums is between 1 and 10⁻4. For edge cases, if n equals k, each subset will have a size of 1, and the total incompatibility will always be 0 since each subset contains only a single element. On the other hand, if the array contains duplicates that make it impossible to divide into k subsets without repeating elements in the same subset, the output must be -1. Efficient algorithms are necessary for larger values of n and k to ensure the solution runs within acceptable time limits. To solve the problem of determining the minimum incompatibility when dividing an array into subsets, we first considered the brute force approach. The intuition here is straightforward: generate all possible partitions of the array into subsets of equal size, calculate the incompatibility for each subset, sum them up, and return the minimum total incompatibility. While conceptually simple, the implementation relies on recursion or backtracking to explore all possible partitions. However, this method quickly becomes computationally prohibitive. Generating all partitions is exponentially complex, and with n going up to 16, the sheer number of combinations makes this approach infeasible for larger inputs. It's a good starting point for understanding the problem, but we need something far more efficient. To improve efficiency, an optimized backtracking approach with pruning was considered. Here, instead of blindly generating all partitions, we introduce pruning to discard invalid or suboptimal branches as early as possible. For instance, if a subset violates the rule that all elements must be unique, we can terminate that path immediately. This approach incrementally builds subsets, ensuring that each subset is valid before proceeding further. Sorting the input array, nums, also plays a role in reducing redundant computations and improving efficiency. While this optimization significantly reduces the number of paths explored, making it much faster than brute force, it's still exponential in the worst case. Additionally, managing the constraints and edge cases can make the implementation quite complex. Another promising approach is dynamic programming with bit masking. This utilizes a bit mask to represent the state of the partitioning process and stores intermediate results to avoid redundant calculations. By dividing nums into subsets and minimizing incompatibility, this approach iteratively refines the solution. The DP table, indexed by bit masks, tracks which elements have been used. From each state, we generate possible subsets, calculate their incompatibility, and update the DP table accordingly. While the time complexity involves exponential factors, it is much more feasible for the given constraints of n equals 16. However, the challenge lies in carefully managing the bit masking and subset generation. The chosen strategy for this problem is dynamic programming with bit masking because it offers the best balance between performance and feasibility. While backtracking with pruning is simpler to understand, it still struggles with efficiency for larger inputs due to the lack of reusable computations. On the other hand, the DP approach leverages overlapping subproblems, allowing us to significantly reduce redundant calculations. This makes it the most efficient option for the given constraints. A key insight that simplifies this approach is recognizing that the problem boils down to finding valid partitions of nums into subsets. Using a bit mask, we can efficiently track which elements have already been included in subsets. Sorting the input array helps maintain a consistent order when generating subsets, which not only ensures correctness but also simplifies the implementation. Another critical realization is that the incompatibility of a subset depends solely on its elements. This means we can pre-compute the incompatibility for all possible subsets and reuse these results during the DP process, further improving efficiency. In weighing the trade-offs, backtracking with pruning is easier to implement but becomes impractically slow for larger inputs because of its exponential complexity. On the other hand, dynamic programming with bit masking, while more challenging to implement, is significantly faster and scales well within the given problem constraints. Both approaches require careful handling of edge cases, such as ensuring that nums can indeed be divided into valid subsets. Ultimately, the DP approach with bit masking stands out as the most efficient and scalable solution. It balances implementation complexity with performance, making it the preferred choice for solving the problem of minimum incompatibility effectively. The problem requires us to divide an array, nums, of size n into k subsets, each containing m equals n/k elements. The goal is to minimize the sum of incompatibilities across these subsets, where the incompatibility of a subset is defined as the difference between its maximum and minimum values. If it's impossible to partition the array into subsets of size m, such as when n isn't divisible by k, we return -1. To tackle this, we start by conducting some preliminary checks. First, if n%k equals 0, we immediately return -1. Next, we calculate m and check if any number appears more than k times in nums. If it does, it's impossible to distribute it across k subsets, so we return -1. To represent the state of our solution, we use bit masking, where a bit mask of size 2n tracks which elements in nums have already been used. We also define a dynamic programming array, DP mask, where mask represents a subset of elements and DP mask stores the minimum incompatibility achievable for that subset. We initialize our dynamic programming table with DP 0 equals 0, indicating that no subsets yield 0 incompatibility. All other entries in DP are set to infinity initially, as we haven't computed their values yet. To populate this table, we iterate through all bit masks from 1 to 2n1. For each bit mask, we check if it represents a valid subset of size m. If it does, we calculate the incompatibility of the subset as the difference between its maximum and minimum values. Then, we update DP mask by considering all possible combinations of prev_mask, where prev_mask represents previously used subsets that don't overlap with the current subset. Specifically, we update dp mask or prev_mask to be the minimum of its current value and the sum of dp prev_mask and the incompatibility of the current subset. Finally, the result is stored in dp1n1, which represents the scenario where all elements are used. If no valid partitioning is possible, we return -1. This approach relies on several key insights. First, bit masking provides an efficient way to represent subsets and ensures that all combinations of subsets are considered without redundancy. Second, dynamic programming helps store the minimum incompatibility for each subset configuration, avoiding repeated calculations for overlapping subsets. Additionally, pruning is performed upfront by checking the frequency of numbers in nums. If any number appears more than k times, we can eliminate those cases early, saving computational effort. Lastly, we use a systematic approach to generate subsets of a specific size, m, by iterating over bit masks, which allows us to avoid explicitly generating all possible subsets of nums, further improving efficiency. To implement the algorithm, we use three main data structures. First, bit masking is represented using integers, where each bit in the integer indicates whether an element in nums is included in the current subset. For example, if nums equals 1, 2, 3, 4, and the bit mask is 1101, it represents the subset 1, 3, 4. Second, the dynamic programming table is an array dp mask, where each entry stores the minimum incompatibility for the subset represented by the corresponding bit mask. This array has a size of 2n, where n is the size of the input array. Finally, a frequency map, implemented as a hash map, tracks the frequency of each number in nums. This ensures that no number is used in more than k subsets, which would violate the constraints. Analyzing the complexity, the algorithm iterates through all subsets represented by 2n bit masks. For each bit mask, it processes subsets of size m, and calculating the incompatibility for a subset takes m time. This makes the overall time complexity 2 to the power of n*m. In terms of space, the dp array requires 2 to the power of n space, while additional space is used for the frequency map and temporary subsets. Several edge cases must be handled carefully. For instance, if n%k equals 0 or if any number in nums appears more than k times, the partitioning is impossible. Duplicates in nums also need to be managed to ensure subsets remain valid. Finally, when dealing with small input sizes, such as n equals 1 or k equals 1, the algorithm should gracefully handle these scenarios and return the correct output. Let's walk through an example to solidify our understanding. Suppose the input is nums equals 1, 2, 1, 4, and k equals 2. First, we perform the prechecks. Here, n equals 4 and m equals 2, which satisfies n%k equals 0. Additionally, no number appears more than k equals 2 times, so partitioning is possible. Next, we use bit masking to generate all subsets of size m equals 2, such as 1, 2, and 1, 4, and calculate their incompatibilities. Using dynamic programming, we populate the dp array to store the minimum incompatibility for each valid combination of subsets. After processing all bit masks, the result is stored in dp1n1, representing the minimum incompatibility when all elements are used in k subsets. For this example, the output is the minimum incompatibility value achievable for the given input. This Python implementation solves the problem of dividing an array nums into k subsets of equal size while minimizing the total incompatibility. Here's a detailed explanation of the approach. 1. Preprocessing and validation. The algorithm first calculates m, size of each subset, as n/k. Using a counter, it checks if any number in nums appears more than k times, which would make the partition impossible, returning -1 early. 2. Dynamic programming initialization. A dictionary dp is used to store the minimum incompatibility for each subset mask. Initially, dp is set to 0, 0, representing the starting state with no subsets formed. 3. Iterating over mask states. The algorithm iterates through all possible bit masks up to 2n1, where each bit mask represents a subset of nums. A subset is valid if it contains exactly m elements and all elements are unique. For subset incompatibility calculation, for a valid subset, the incompatibility is calculated as the difference between the maximum and minimum values of the subset. The algorithm then updates the DP state by combining the current subset with previous subsets, ensuring no overlap using bitwise operations. 5. Final result. After processing all masks, the algorithm checks DP for the final answer corresponding to a mask with all elements used. If no valid solution exists, it returns -1. This approach leverages dynamic programming and bit masking to efficiently explore all potential partitions while minimizing incompatibility. The time complexity is exponential in the worst case due to the bitmask generation but is manageable for small input sizes due to pruning and validation checks. Here, we start with the Java implementation of the minimum incompatibility problem. First, we import the necessary libraries and define the method minimum incompatibility. The input parameters are an integer array nums and an integer k. We calculate the length of the array n and determine m, which represents the size of each subset, as n/k. Next, we create a frequency map using a hash map to count the occurrences of each number in the array. This is crucial because if any number appears more than k times, it would be impossible to distribute it across k subsets without duplicates, so the function immediately returns -1 in such cases. After validating the frequency constraint, we move to the dynamic programming setup. The maxmask variable, calculated as 1n, represents the total number of possible subsets of the nums array. We initialize the DP array with integer.max_value to act as our state storage, where DP, mask, holds the minimum incompatibility for the subset represented by mask. Finally, we set DP 0 to 0 since the empty set has no incompatibility. The outer loop iterates over all possible masks, and we process only those where the number of elements in the subset is divisible by m. Now, we gather the elements represented by the current mask into a subset list. This is done by iterating through all bits of the mask and adding the corresponding elements from the nums array when the bit is set. Once the subset is formed, we check if it is valid. It must have exactly m elements, and all of them must be unique. To ensure uniqueness, we compare the size of the subset with the size of its conversion to a hash set. If the subset is valid, we calculate its incompatibility as the difference between the maximum and minimum elements of the subset. Next, we attempt to combine this subset with all previously computed subsets. By iterating through prevmask, we ensure that the current mask and prevmask do not overlap, and we update the DP value for the new combined mask. The new value is the minimum of its current value and the sum of the incompatibility of the prevmask subset and the current subset. After processing all possible subsets, the result is stored in DP, maxmask1, which represents the entire array. If its value remains integer.max_value, it means no valid partitioning was found, and we return -1. Otherwise, we return the computed minimum incompatibility. To solve this problem, we need to divide the array nums into k subsets of equal size, ensuring that the sum of the subsets' incompatibilities is minimized. The incompatibility for a subset is computed as the difference between the maximum and minimum values in that subset. If it's not possible to divide the array into such subsets, the output should be -1. For example, if nums is 1, 2, 1, 4, and k is 2, the array length is 4, so each subset must contain m equals n/k equals 2 elements. Using the frequency count of the array, we see that no number appears more than k times, which means dividing the array is feasible. We initialize a dynamic programming dictionary DP with 0, 0, where the keys represent bit masks for subsets, and the values store the minimum incompatibility for those combinations. The next step involves iterating over all possible bit masks from 1 to 2*n1, where each bit mask represents a subset of the array. For instance, consider the mask 3, binary 0011, which corresponds to the subset indices 0, 1, and the elements 1, 2. The incompatibility of this subset is calculated as max 1, 2, min 1, 2 equals 1. We then update the dynamic programming table by combining this mask with all previously computed masks. For example, combining mask equals 3 with prev_mask equals 0 gives new_mask equals 3, and the DP value is updated as DP3 equals min DP.get 3 inf DP 0 plus 1, resulting in DP equals 0 0 3 1. This process is repeated for all masks, ensuring that only valid subsets are considered, those with exactly m distinct elements. For another example, the mask 12, binary 1100, represents the subset 1, 4, with an incompatibility of 3. This mask is also combined and updated in the DP table. Once all valid masks have been processed, the final result is obtained from the DP table. The full mask, representing the entire array, is 1n1. For the example where nums equals 1, 2, 1, 4, and k equals 2, the full mask is 15, binary 1111, and the minimum incompatibility stored in DP, 15, is 4. Now let's look at another example where nums equals 6, 3, 8, 1, 3, 1, and k equals 3. Here, n equals 6, so m equals n // k equals 2. The frequency count of the array shows that no number exceeds k occurrences, so the division is valid. For a mask like 5, binary 0101, the subset 6, 8 has an incompatibility of 2, which is then used to update the DP table. Similarly, for mask equals 10, binary 1010, the subset 3, 1 also has an incompatibility of 2, and the DP table is updated accordingly. After processing all masks, the full mask for nums equals 6, 3, 8, 1, 3, 1 is 63, binary 111111, and the minimum incompatibility is calculated from the DP table. The result for this example is 4. Finally, consider an example where nums equals 1, 2, 3, 4, and k equals 1. Here, the entire array forms a single subset, as m equals n // k equals 4. The incompatibility for this subset is max 4, 1, min 4, 1 equals 3, so the output is 3. This demonstrates how the approach handles different cases by leveraging the dynamic programming table and bitmasking to efficiently compute the minimum incompatibility. To analyze the time complexity of our solution, let's break it down step by step. First, we have the outer loop that iterates over all possible subsets of the nums array, represented by the all_masks variable. With n elements in the array, there are 2 n possible masks, meaning this loop runs 2 to the power of n times. Next, for each mask, we construct its corresponding subset, which involves iterating through all n indices to determine which elements are included. This step takes n time. Additionally, we validate the subset by checking if its size equals m and if its elements are distinct. Using isSet to ensure uniqueness and checking its length adds another m time, where m is equal to n/k. Finally, for each valid subset, we update the dynamic programming dictionary DP by iterating over its current entries. In the worst case, there could be up to 2 to the power of n entries in DP, and checking if masks overlap takes constant time per entry. Now, considering all these steps together, the total complexity comes from the combination of the nested loops and operations. The outer loop runs 2 to the power of n times, and for each mask, the subset construction and validation take n plus m. The inner loop over the DP dictionary adds another 2 to the power of n in the worst case. Multiplying these, we get an overall time complexity of 2 to the power of n asterisk, n plus m, plus 4 to the power of n. Since 4 to the power of n dominates, the final time complexity simplifies to 4 to the power of n. For space complexity, the primary contributor is the DP dictionary, which stores the minimum incompatibility for each valid mask. With up to 2 to the power of n masks, the space usage is 2 to the power of n. Additionally, auxiliary variables such as the subset list and the count array require n space. Together, the total space complexity is dominated by the DP dictionary, resulting in 2 to the power of n. To summarize the total space complexity, the dominant factor is the DP dictionary, which leads to an overall space complexity of 2 to the power of n. Comparing our optimized approach to a brute force solution highlights its efficiency. A naive approach would involve generating all possible partitions of nums into k subsets of size m, calculating their incompatibility for each partition. The number of ways to partition n elements into k subsets is governed by the Stirling numbers of the second kind, which grow exponentially with n. This makes the naive approach computationally infeasible for larger values of n. In contrast, the current solution leverages bit masking and dynamic programming to explore valid subsets more systematically, avoiding redundant calculations. While still exponential, this approach is much faster than brute force due to optimized state management and subset validation. Looking at the best, average, and worst cases, the algorithm's performance remains consistent across scenarios. In the best case, where all elements in nums are distinct, subsets can be formed without overlap or additional checks, but the algorithm still explores all 2n masks, maintaining a time complexity of 4 to the power of n. In the average and worst cases, the algorithm evaluates all possible masks and subsets to ensure correctness, resulting in the same 4 to the power of n complexity. The mathematical justification for this exponential growth lies in the need to construct and validate all subsets, represented by the 2n masks, and to update the DP state for each valid subset. The inner loop over the DP dictionary further compounds this, leading to a final time complexity of 4 to the power of n. Space complexity is proportional to the number of masks, resulting in 2 to the power of n, space usage due to the DP dictionary. When solving this problem, there are several common mistakes to avoid. First, always validate the division constraint. If the size of the array, denoted as n, is not divisible by k, then it's impossible to divide the array into k subsets of equal size. Skipping this check can lead to unnecessary computations or incorrect results. Next, be careful to ensure that subsets do not contain duplicate elements. If duplicates are allowed, the calculated incompatibility will be incorrect, so always verify elements during subset selection. Another mistake is using an inefficient state representation in dynamic programming. For example, tracking subsets with a list instead of a bitmask can lead to excessive memory usage and redundant calculations, slowing down the solution significantly. Finally, a purely greedy approach, like always picking the smallest unused element, might seem intuitive but often fails. This is because it doesn't explore all possibilities or backtrack to fix earlier decisions, which is critical for finding a valid solution. Now, it's important to consider the problem constraints on maximum size. For example, when n is less than or equal to 16 or k is less than or equal to 8, the problem is often designed to be solved using combinatorial methods such as bitmask dynamic programming. Ignoring this can lead to inefficient brute force solutions that exceed time limits. A key insight here is recognizing that this problem requires partitioning the array while minimizing the maximum difference in each subset. This hybrid nature of combining combinatorics, dynamic programming, and greedy strategies is crucial for success. To optimize, you can use bitmasking to represent subsets and track states in dynamic programming. This drastically reduces redundant calculations and optimizes memory use. Stay flexible, as interviewers might alter the constraints, such as allowing unequal subset sizes or changing the metric to minimize. Lastly, be prepared to discuss trade-offs between different approaches, like brute force, backtracking, and dynamic programming. Highlight their time complexities and scalability as n and k grow. This problem shares similarities with other partitioning problems, which can help you build intuition and refine your approach. For instance, in LeetCode 698, partition to k equals some subsets, the goal is to divide an array into k subsets, but with equal sums instead of minimizing incompatibility. Another related problem is LeetCode 473, match sticks to square, where the subsets must form the sides of a square, introducing geometric constraints. LeetCode 78, subsets, is a simpler problem where you generate all possible subsets of an array, making it a great starting point for understanding subset generation. Lastly, LeetCode 2820, partition array according to given criteria, is a variation that focuses on partitioning an array based on different, defined constraints. Studying these problems can give you a broader perspective on solving partitioning challenges. There are several alternative approaches to solving this problem, each with its own trade-offs. One straightforward method is brute force combined with validation. This involves enumerating all possible partitions of the array into k subsets and calculating the incompatibility for each. While simple to understand, it is computationally expensive, with a worst-case complexity of n. A more efficient option is backtracking, where subsets are built incrementally while ensuring constraints are satisfied. This is faster than brute force but can still be exponential in time complexity unless effective pruning is applied. Dynamic programming with bit masking is another option. Here, subsets are represented using bit masks, and DP is used to track the minimum incompatibility for each state. This approach significantly reduces redundant calculations but comes with higher implementation complexity and a time complexity of 2 to the power of n*n. Lastly, greedy heuristics can be used to assign elements iteratively based on minimizing incompatibility. While this method is fast, it doesn't guarantee an optimal solution, making it less reliable for certain cases. Great job! We've successfully reviewed the minimum incompatibility problem. We discussed the approach, complexity, and key takeaways. Keep practicing, and remember to subscribe for more. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!